In this video, I'm going to look at constant acceleration in 2 and 3 dimensions. If you're looking for variable acceleration, which uses calculus, just click the link below. I've set up a 1, 2 and 3D version of the same question so you can see how they compare. In the first question, initial velocity is 3 and acceleration is 1. In the second scenario, I've added minus 2j and plus 3j for the second dimension. And in the third scenario, I've added 1k here and 0k here, which just means there's zero velocity in the third dimension. Often in documents, this format of ijk is used because it's a bit fiddly to put column vectors in, but sometimes it's easier to work with column vectors. So I've actually done the column vector format here. That's what I'm going to use in this scenario. Notice that here I didn't need to write the k, but when you write the column vector format, you do need to write the k. So as usual, I'm going to read through the question and write down the key values. A particle starting from the origin has initial velocity u and acceleration a. Now those would be given in the question normally, but as I've got 3 different sets here, I've written them down in my list format already. Find the velocity and the position after 4 seconds. Sorry about the thunder in the background. There's a bit of a storm going on. 4 seconds, so t equals 4, which is just a scalar quantity. So I've written that doesn't change in the 3 scenarios. We've got to find velocity and position after 4 seconds. So first of all, velocity. This is constant acceleration. So in that case, we're using v equals u plus a t because we have u, a and t. I've already done the 1D version for both of these, as you'll have seen those before anyway. So v equals u plus a t, which gives 7 meters per second. For the second part, we need to find the position, and I'm going to use the position vector format. R equals ut plus half at squared. The full version of that formula, the position vector formula, gives the position relative to the origin. That's why it's called R. And it is very similar, as you can see, to the formula here, but it just has R of 0, which means the initial position, or the position at time, equals 0. Now in our question, the particle is starting from the origin, so R of 0 is 0, so I'm just using a scaled down version of that formula. So now I'm going to, if we just check the 1D version, ut plus half at squared gives 20 meters. So I'm going to do the 2D versions of both of these and compare them to the 1D. So v equals u plus a t, and we just have to treat each row of the vector as a completely separate equation, remembering that when you're multiplying a vector by a scalar, each component of the vector has to be multiplied by the scalar. So 3 plus 1 times 4 is 7, and negative 2 plus 3 times 4 is 10. So you can see that the first row of this vector is exactly the same as the 1D version. Now I'm going to do this, the position. So that's u t plus half a t squared. So when I multiply that through, I get exactly the same as I did for here because it's the same calculation. And then for the second row, negative 2 times 4 plus a half times 3 times 4 squared is 16 meters. And as you can see again, the 1D version is exactly the same as the top row of that 2D vector. I've already done the 3D version. Just to compare, we've now added the second dimension here. So the first two rows are exactly the same in each of these cases, and the third row then is added for the third dimension. 1 plus 0 times 4 is 1, and 1 times 4 plus a half times 0 times 4 squared is 4. Just going back to the position vector formula, if, say, the particle didn't start from the origin, but a position of 4i plus 5k, how would that change the formula? So if I just slide that to there, you can see that these two terms here don't change. There's just r of 0 added in, because the position here is 4i 5k. And all that does is it changes the 20 for the final answer. We've got to add 4 to give 24, and for the 16 we add 5 to give 21.